As ICT continues to grow year on year, so too does power consumption. Here in Japan, energy use by telecom's data centres is expected to increase to a staggering 10 billion kilowatts by 2012. Now, researchers at NTT have developed technologies that can reduce this by 15%. Within a data centre, about 45% of mains power is used by the ICT equipment itself, such as servers, routers and storage, with 40% being used for air conditioning. These facilities rely on backup power via DC-powered batteries, and today that means 4 stages of power conversion, with up to 10% power loss at each stage. The NTT solution uses high-voltage direct current, which reduces this to 2 stages. What's more, installations can use smaller diameter cabling, which reduces installation costs. The mains power supply is first stepped down, then passed through this rectifier which converts the AC power into DC power. Now, some of that DC is used for the backup batteries, but the rest of it goes through this special HVDC power distribution cabinet, and from here it's then channelled along the smaller cables into the various pieces of ICT equipment. With 40% of data centre power use taken up by air conditioning, NTT has devised 2 solutions that can reduce this unwanted burden. The first is known as aisle capping. This optimises airflow within data centres by designating discrete channels. You have the hot channel for the hot exhaust air generated by the racks of equipment, and next to the hot channel you have separate and sealed cold channels, which creates the ideal operating environments. The cold air is fed up through the raised floor directly into the cold aisle, and the hot exhaust air from the equipment stays outside and doesn't recirculate. That way you don't have to crank up the air conditioning to maintain a favourable environment, and all this is measured through these thermocouples. The second new method is called rack-type air conditioning, and this has been designed to solve the problem of local hotspots caused by large heat-generating equipment such as blade servers. Now, in this case, a special rack-mounted air conditioner is placed directly opposite the server, and it pulls hot air through an air-cooled system and blows cold air directly onto the targeted server. And when used with the air capping scheme, big savings in energy use can be achieved. Plus, it doesn't need water to operate, and it's highly efficient because the inlet air is actually the high-temperature exhaust air from the hot aisle.
To help build a sustainable society, NTT Group promotes R&D in environmental technologies on a variety of fronts, such as high-voltage direct current power systems, supply systems for energy conservation, solid oxide fuel cells for clean power generation systems that use natural resources efficiently, and methodologies for evaluating environmental impact based on life cycle assessment.
Recently, Sun Microsystems unveiled its green data center in Bloomfield. It has reduced its CO2 emissions by up to 11,000 metric tons per year and shrunk its carbon footprint by about 6% in the US. This new revamped and consolidated facility is the company's largest green IT project to date.
We spent about 4.5 years getting our portfolio under control. And we realized that we've got to really reinvent how we're going to go back and design data centers. Because one of the beauties of my job is all the next generation products that are going to our data centers for our customers in 2 to 3 years are in my data centers first. And so we really have to solve the density challenges beforehand. So if you notice, we're inside of a traditional data center with a raised floor and cooling units on the wall. And so they usually blow cold air down. It comes up through these aisles. And then it goes through the servers, comes out, and finds its way back to the actual cooling units. So that's the traditional way. The problem is, what happens if you have a 30 kilowatt server next to a 1 next to a 2? You can't cool them all the same way. And so we have deployed closely coupled cooling. And so this is an example. This is a Liebert XD, or extreme density unit, and they call it a Liebert XDV, vertical. And it basically blows cold air out the front. It sucks in the server. The heat comes out the back, and then it returns on the back of the unit. So it now neutralizes the heat at the source. This is refrigerant-based, and it's also modular. So now I can just snap it in, plug it into the refrigerant piping, and I have 10 kilowatts of cooling wherever I want it to be at.
Modularity enables efficiency. It also enables agility for the company.
So if I am able to now snap in the cooling, power, and connectivity components to expand or contract when I need to, and they're all efficient no matter what load is in there, then business climate can change and I can adapt to that very quickly. So this is two 1,000-ton chillers. They're highly efficient, they're variable. So traditional data centers have a primary secondary loop, which means the primary loop is constant flow and you're wasting energy for that water, and then it's variable inside the building. What we have is a variable primary loop, which means that it's all one big loop inside and outside of the building, and all the components along that loop actually match the load that's sensed. So these chillers will go up and down based on whatever is generated inside the data center. The fact that we now can continue to grow with that and keep our PUE of 1.28 is critical, because we are at lower densities today, but as we scale up, our PUE will stay constant. So our data center starts at 9 megawatts, scales to 16, and then scales to 21. And if you look at the yard itself, I can now snap in chillers, transformers, and double my power. I can do chiller towers, generators, pumps, everything I need to expand with no major construction. In the past, when we'd try to roll in new equipment in a data center, the real estate side would have to take 8, 12, 16 weeks to go back and get something fit up for it. That's if they had power and cooling to do it. Now with modularity, everything is built for scale. So I can snap in cooling units at the pod inside the room, or I can snap in chillers in the plant to be able to scale up where I need to. And it's going to now match the load that's in there. So even though they roll in more equipment, we're still keeping our efficiencies there. Our PUEs stay the same. And even at 40 or 50% load, we're still getting those efficiency levels. And as we start to go up in load, we're still maintaining that efficiency.